Hello, welcome to this video about our EV10AS940 ADC. EV10AS940 ADC is the only device offering both 35 GHz direct conversion and single-ended input. Single-ended input removes the need for balloon and associated distortion effects. Moreover, it allows both space reduction, costs and time saving. EV10AS940 gives sufficient instantaneous bandwidth to accommodate all applications, frequency plans, while optimizing sampling rate, data stream and power consumption. More specifically, EV10AS940 shows minimal distortion up to K-band with typical dynamic performances of 44 dBc SFDR at 28 GHz at -6 dBFS and 38 dBc SFDR at 35 GHz at -6 dBFS. Satellite wideband application like telecom system will benefit from EV10AS940's superior NPR performance till K-band. Zooming into the digital features, AS940 has been designed for military systems such as electronic warfare, secure microwave data links, advanced radars, LPR radar thanks to its fast frequency hopping capability, 30 nanoseconds, and its deterministic latency high-speed serial interface EasyStream. Its digital down conversion channels reduce and optimize the data stream and HSSL's usage on the FPGA side and enables to connect more ADCs to the same FPGA. Finally, EV10AS940 embeds a scalable chain sync to synchronize several ADCs and perform beamforming, extended instantaneous bandwidth, or other specific use case requiring high accuracy sampling phase control. EV10AS940 is based on time interleaved SAR ADCs with on-chip calibration. Interleaved SAR ADCs introduce offset and gain mismatch if left uncalibrated, so a non-chip calibration system is used to estimate and compensate the two mismatch sources. It provides excellent linearity across the wide temperature and frequency range. It adjusts automatically to the input signal frequency range. There are two types of calibration: factory with two subtypes, the global and local factory calibration, and the background calibration. Each calibration can be activated or deactivated individually. Total calibration correction coefficients are visible in registers of the ADC. The factory calibration coefficients, global and local, are stored in the OTP memory during factory calibration procedure. The global factory calibration uses the same coefficients for all SARs. The local factory calibration uses different coefficients for each SAR. Local factory coefficients are modifiable. The background calibration is based on a continuous calculation that can run at the same time as the component is converting input data. For each one of the interleaved cores, the average and RMS values of the output are estimated on a sliding time window. The only condition is that an input signal must be present, otherwise the gain cannot be estimated. The input signal can be a sine wave, a modulated signal, or a wideband signal. Note that if a single-tone sine wave, its frequency must not be a multiple of fs over 64. Otherwise, the signal at the conversion core level is interpreted as offset and the local calculations are misleading. The drawback of this background calibration, apart from the conditions of the input signal, is that the average on RMS calculations impact power consumption, around 250 milliwatts. Note that the coefficient stored in the OTP memory for the factory calibration can be used as starting point for the background calibration. The advantage of the background calibration is that it tracks the circuit evolution versus temperature and time. Let's start by describing the bench that will allow us to explain and demonstrate the performances of the on-chip calibration. We have here our Teledyne AS940 FMC evaluation board, a mezzanine FMC Plus board, connected to our FPGA carrier board with the AMD Kintex UltraScale KU35 FPGA. Around this board we have two SMA 100-bit signal generators from Roden Schwartz and a PC with our GUI developed for ADC evaluation purpose. Let's get started. The powering up of the bench is not part of this tutorial and was explained in a previous video. You will find the link for the video below. After powering up, launch the GUI, click on the connect icon to connect the board, check that the socket icon turns green. This indicates that the AS940 board is detected. Click on the judge button and ensure that the IDs correspond to expected values indicated in the user guide. Enter the F-clock frequency. For this tutorial is external 12.8 GHz. The GUI can be used to calculate the correct frequency for the FIN chosen. We will pass through the correct frequency settings that are explained in a previous video. So, we will use here the correct frequency calculated for FIN 8.8 GHz. Then, to have all-in-one configuration, press the Init Sequence button. This will perform a reset, clock synchronization and load optimal settings in the AS940 at once. This also activates the background calibration of the ADC. At this stage, the clock is set up. Now we will demonstrate the performance of the on-chip calibration. To modify the calibration settings, click on the calibration icon on the duty control window. On this window, it's possible to enable, disable local factory, global factory and background calibration, to modify the coefficient value and to modify the steps. Background calibration step correspond to the gain and offset step of the algorithm. It is recommended to set it to 0, corresponding to the fastest calibration conversions. Click on refresh to see the total correction values. The total values should not be too close from their limits, -6.25 plus 6.25. Note that the Init Sequence button mentioned previously activates the background calibration, but does not refresh the calibration choice view showing which type of calibration is active. The background calibration effect can be illustrated in this example. Let's deactivate all the calibration. Here, the acquisition results without any calibration. On the top left is displayed the first 10 nanoseconds of acquired data. On the top right is the histogram of all codes acquired. On the bottom, the spectrum with the main spurs. The spectrum shows a lot of spurs which are, for the vast majority, interleaving spurs in the form of n by f clock over 32, with plus minus fin contributions. So now, the same acquisition performed after activating the background calibration. With a step of 0. The effect of the background calibration appears clearly with the removal of the interleaving spurs. The most relevant figure of merit is the tilt strongly improved from 32.7 to 43.6 dBc. The SFDR, dominated by the FC 6/8 improves moderately from 38.5 to 44 dBc. The main remaining spurs are then the H2, H3 and FC/2 minus Fin, which are almost always responsible for the SFDR. The next step displayed on this screenshot will not be demonstrated here, but explains the influence of the gain and offset correction individually. To reduce power consumption, the background calibration can be activated periodically and recorded in the local factory. In the GUI, to use the local factory calibration with coefficients from the background calibration, click on Background to LCO button. Slight differences can happen between the values due to rounding effect. We have reached to the end of this video. We go through the on-chip calibration of a EV10AS940 ADC and its impact on the ADC performances. The global factory, local factory and background calibrations allow to have easy and tailored calibration for each application and environment. The evaluation board is available so you can start evaluation and tests right away. If you have questions or if you are interested either on the EV10AS940, please contact us using Teledyne E2V hotline email address.